Hello everyone, today we are going to practice logistic regression together. We'll start by reviewing linear regression and smoothly transition to logistic regression. We'll derive the log loss function from scratch and build an energy model. Before we begin, please ensure you have watched the video lessons on the theoretical aspects and implementation of linear regression with zero. Let's start by recalling ordinary linear regression, as discussed in the previous lesson. The linear regression line has a slope coefficient, denoted as coefficient A, and an intercept coefficient, denoted as coefficient B. The slope coefficient in linear regression indicates how steep the slope angle is with respect to the feature x. While linear regression deals with regression problems, today we're focusing on classification and the logistic model. Let's generate some data by creating two circles, each consisting of 50 objects with two attributes, and assign them to two classes. We'll standardize the data for the linear model, as it requires scaled data. After initializing and training the standardization scalar, we'll transform our data sample to ensure it's standardized. For standardization, the mean should be 0 and the standard deviation should be 1. Once the data is standardized, training the linear model should proceed without any issues. When we plot our data, we'll see two classes represented by the circles. While we can draw a line, it won't be a prediction of the target value, but rather the regression line itself, which is the product of the feature and its coefficient. Here, when the weight is equal to 1 and the bias term is equal to 0, the prediction lies on the line. We don't need predictions on either side of the line. Technically, our linear model linear regression can act as a separator, similar to logistic regression, but as a linear classifier. However, logistic regression is not yet a fully fledged regression model, but only a linear classifier at this stage. Now, let's consider data where we use linear regression for classification. We'll take 25 points with one useful attribute, and one useless attribute fixed by randomness. We'll have one cluster for one class, and the class separability is evident. Since the mean is not 0 and the standard deviation is not unity for the 25 data points, let's standardize the data and then verify if the standardization was successful. Let's plot our points. Since they are one-dimensional, the y values will be equal to 0 everywhere. To visualize them using any Python visualization library, we need to add another axis. So I'll fill everything with zeros. This additional axis acts as a constant term in our regression model. Now, if we try to draw a line through these points without any slope, it won't fit the data at all. This indicates that linear regression cannot be used effectively in this case. Let's add a minimal slope to the line. The equation for our linear regression becomes 3x plus 0, where the slope coefficient is 3 and the intercept is 0. With this slope, we can at least roughly separate the purple points from the yellow ones. It's not perfect because there are 4 purple points within the territory of the yellow class. Next, let's train the logistic regression model. We'll initialize the model, train it on our data, and obtain the slope coefficient and intercept. We'll denote these as the slope and shift coefficients, respectively. The predicted values from our logistic regression model can be obtained by multiplying the slope coefficient by the feature and adding the intercept. In summary, we'll visualize the linear regression line we obtained, which is not a true regression line but rather the result of applying logistic regression. The coefficients we obtained represent a kind of linear regression applied to the features, with the addition of a bias term. We can evaluate the accuracy of this model by quickly calculating the proportion of correct answers, which turns out to be 0.8. To make predictions using logistic regression, we can apply the sigmoid function to our data and obtain probabilities. Alternatively, we can use the coefficients we obtained and perform the same operations as before: multiply the coefficients by the features, add the bias term, and apply the sigmoid function. While logistic regression does not directly predict classes, we can interpret the results. For example, if the predicted value is negative, it corresponds to one class, and if it is positive, it corresponds to the other class. In our case, we see that the predictions for the first two objects are the same, as are the predictions for the fourth and fifth objects. This indicates some level of dependence in the data, where negative linear regression values correspond to one class and positive values correspond to the other. Now let's build our classifier using the target values obtained from the model. We'll use the feature x as our input and y as our class label. The model will separate the violet points from the yellow ones based on its predictions, and also examine the predicted probabilities, which indicate the likelihood of belonging to each class. We'll obtain two arrays with 2 columns each. The left column represents the probability of being in the purple class, while the right column represents the probability of being in the yellow class. These probabilities sum up to 1, indicating that each object is either purple or yellow. For visualization, let's focus on the probability of being in the yellow class. We'll consider only the first column of the predicted probabilities. Plotting these probabilities, we'll see a curve that is not exactly a straight line, unlike the regression line we saw earlier. By applying the sigmoid function to our linear regression predictions, we transform the linear regression model into a logistic regression model. This transformation allows for classification, with a default cutoff above which objects are considered to belong to the yellow class based on their predicted probabilities. Now let's compare the two models to determine which one is better suited for our data. We'll create a model with slope coefficient 3 and intercept coefficient -2 for our linear regression, which serves as a separator between the two classes. Additionally, we'll take the sigmoid function to create a gentler blue line. In contrast, our implementation of linear regression will produce a steeper orange line. We'll compile all our data into a table, including the objects, features, real target values, and predicted probabilities. For the model, we'll have the predicted probabilities, and for our model, we'll have the probabilities as well. We'll also include the real target classes and determine the cutoff above which objects are considered to belong to the target class. By comparing the predicted probabilities for the model and our model, we can determine the predicted class. If the predicted probability of being in the yellow class is less than 0.5, the prediction will be the 0 class. Conversely, if the predicted probability of being in the target class is greater than 0.5, the model will predict the first class. We can already observe a difference in the predictions, where the best model version predicted the probability of being in the yellow class more confidently, while our model predicted the purple class more confidently. Analyzing the errors made by each model, out of the total 25 objects, the best model misclassified 5 objects, while our implementation misclassified 8 objects. The best model correctly classified 20 objects, whereas our implementation correctly classified 17 objects. To determine which model is more meaningful, we can calculate the likelihood. Likelihood indicates how likely each point in the training dataset is to be part of the law found by the model. Let's consider 3 objects, 2 belonging to the 0 class and 1 belonging to the first class. We'll look at the probabilities predicted by the best model for these objects. For the third object, which belongs to the first class, the model predicts with a 60% probability that it is in the yellow class. This prediction is correct, so the model has guessed correctly. The likelihood for this object is 0.6. For the second object, which belongs to the 0 class, the model predicts with a 10% probability that it is in the yellow class. This prediction is quite unlikely, so it is more likely to belong to the 0 class. The probability of being in the 0 class according to the model for this object is 0.9. The likelihood for this object is 0.9. For the first object, the model predicts with a 22% probability that it is in the yellow class, and with a 78% probability that it is in the 0 class. The likelihood for this object is 0.78. To calculate the overall likelihood for these 3 points, we multiply these individual likelihoods together, resulting in a likelihood of 0.42. We repeat this process for all points where the real class is the first class, taking the predicted probabilities from the generated or best model. This gives us the likelihood for the first class. Similarly, we do this for all points where the real class is the 0 class, taking the predicted probabilities from the generated model. This gives us the likelihood for the 0 class. We subtract this from 1, thus obtaining the probability of being a negative class. Here we get the probability of being a purple class, which is exactly 0. The model originally predicted us to be a yellow class, which is the target class. When we subtract 1 from 1 to be a yellow class, we get the probability of being a purple class. When we multiply these probabilities, we obtain the likelihood that the points belong to the 0 class according to the law. This likelihood is incredibly small. To demonstrate this, let's first analyze the number of objects and divide it by 25 more of our points. We'll start by applying a logarithmic transformation, and then proceed to divide the number of objects. By introducing a negative sign, we derive a logarithmic loss function. We can verify its accuracy by employing marine metrics to convert real target values into predicted probabilities of the model. This process yields the same value as previously discussed. Now let's take our model and calculate the same thing in a slightly accelerated way. First, we take the first class objects and their real target value of first class, and multiply them by each other. Then we multiply that by the purple class objects of the predicted probability of being a yellow class. Additionally, we multiply all values with each other and take the logarithm of these multiplications. That is the likelihood for all our points for yellow and purple. Then we take the minus sign and average over the number of objects. We get the log loss function for our model. By the way, it turned out to be smaller than the generated version of the model, so we conclude that our found linear model is not the best. Let's write down more formally what we have just done. We went from the likelihood that needs to be maximized to the loss function that needs to be minimized, using the properties of the logarithm. First, the properties of logarithms tell us that the logarithm of a multiplication is the sum of logarithms. We use another property of logarithms, which tells us that the number b raised to the power of c is c times the logarithm of the number b. So we can take our power out of the logarithm into a multiplier for our logarithm, and we get sum of the multiplication of the target value of the logarithm to be the target class. An additional step is to subtract 1 minus the target value and multiply it by the logarithm of the probability of belonging to the non-target class. Let's not forget to take a minus because we have to minimize it. Now it remains to sum up the logarithm for the all objects and take the minus, and divide by the number of objects. This gives us the loss for the generated model, which resembles the same loss that was above, but with a different formula. Furthermore, we can check our second model. We get 0.63, and as seen here in this loss function, it is trained on the logistic regression model. The term logistic regression derives its name from the logistic loss function. Today we've delved into details of logistic regression, gaining valuable insights into its workings. Stay tuned for further enlightening videos on my channel as we continue our journey into machine learning and data science. Thank you for your attention. Goodbye, everyone.